So hi, I'm Brett McGuire. I'm going to be the session chair this morning for astrochemistry and for exoplanets. So since I thought we'd probably be starting a little bit late, I put together a kind of short warm-up talk here, and it's just going to touch on a few different topics in astrochemistry and in exoplanets. It's not meant to be comprehensive. You're going to get the details from the people that are giving the talks today, and it may not actually talk about everything that are going to be in the talks today. It's just supposed to get you thinking about the topic that we're going to be discussing. I don't really plan to stop for questions at the end, but that doesn't mean that you shouldn't stop to either ask questions or, more importantly, give commentary along the way. If there's any experts in the room that want to add something to a particular topic, that would be fine. So just getting started here. In the beginning, there was hydrogen and helium from the Big Bang and a smattering of a few other less interesting things like boron and lithium. That hydrogen and helium formed into the first stars, and then these stars eventually spat out more complicated things. So here's a periodic table I got off of Wikipedia that tells you, it's actually really nicely color-coded, right? The different things that came out of the Big Bang, things that are produced in large stars or have to be made in supernovae, and then of course the fun things down here that we make in labs. So we really had to go through a first generation of processing in stars to get anything more complicated than hydrogen and helium. Eventually, we started looking for things even more complicated than that. Up until the 1930s, so I guess this reference here is 1937, the prevailing wisdom was that there was nothing other than atoms and their ions in space, because it was just going to be too harsh. There's too much UV radiation, there's too much high energy stuff coming out of these stars for molecules to exist. And people that were looking for molecules were kind of shunned to the edges of the field. So there were some folks that said, screw you, we're going to look for them anyways. So this is a spectrum taken with the Mount Wilson Observatory, right there, of CH, the first molecule detected in space. So the spectrum's from 1941. 1937 was when the assignments were made, but there weren't any pretty spectra in the paper, so I couldn't show you those. And then, so there's a timeline there. Over the next few years, they picked up a few more, some very simple ones, CN, CH+, and OH. And then astrochemistry as a field was really born here between 1963 and 1980. This is when radio astronomy came to the forefront. All of these small molecules here were being detected primarily in electronic transitions using visible and infrared telescopes. That's kind of a challenging way to find molecules because you have to have a background light source to absorb against. So you have to have molecules between you and a star, and you have to know what that star's spectrum looks like so that you can register what those dips in the spectra are. With radio telescopes, you can look for the emission from molecules that are rotating and tumbling over in space, and they have a very unique spectra. A unique spectra, not a very unique spectra. So there were 59 more molecules detected in this space, and then since then we've gotten, I put this slide together 2 years ago, so 110. So now we're up to, this number should be like 120 or 130. We're nearing the 200 mark for molecules detected in space. So what is astrochemistry then? Well, I call it the study of molecules in space, where they are, how they got there, and what they are doing. All right, so chemistry does occur in space. It's very different from the chemistry that occurs here on Earth, because you're in a vacuum, you're at low temperatures most of the time, and the time between collisions for molecules is very small. So you can get exciting, energetic, exotic species that don't last for any amount of time on Earth that have very long lifetimes in space, so they can hang out and do interesting things. So how do you build up some molecular complexity in the ISM? For a while, ion molecule chemistry will dominate. And what that means is that you have one neutral molecule and one ion. Right? Space is a very good vacuum, so it's very hard for molecules to find each other to react. If you have one that's charged, that can induce just a little bit of a dipole in the other molecule and pull an attractive force together so that they're more likely to find each other and react. All right, and these ion molecule reactions also have the benefit of being largely exothermic and kinetically favorable. So they go fast and they release energy. They don't take energy input. So it's very good for the cold vacuum regions of space. So you can see here you start with H3+, right? And then you can just start using H3+ to transfer charge all the way up the line. Now this can build up long-chain hydrocarbons up to about HC9N, right? So that's just a long linear chain of molecules, and it can do some organic chemistry. You can get up to about methanol efficiently in the gas phase. But at that point, these ion molecule reactions drop off, and you really can't make anything more complex than that. What you have to do then is turn to these ice surfaces. Right? So you take a dust grain, you freeze out molecules onto the surface, and now you've concentrated all of your rare reactants into one place. And you have a third body, that grain surface, to take away some of the energy. So you can start piecing together more complex things. You take methanol, you bring a cosmic ray in, you break it up into a methyl and an OH, and now you just start clicking blocks together like Legos to build up more complicated structures. And then these ices can be desorbed into the gas phase and detected that way. So astrochemistry, you're going to hear about some different talks today from the different disciplines. There's laboratory astrophysics. These are the people that measure the spectra of molecules in the lab, measure how they react with one another, the rates and the thermodynamics. There's the observational astronomers that go out and look for the molecules, tell us which ones are there, how many are there, how excited are they. And then astrochemical modelers that try to take the information from both of these groups, piece them together, and say, well, you have this soup of molecules, what can you make next? What does this tell us about the chemistry occurring in the region? So we're also going to talk about exoplanets today, and molecules have been found in the birthplace of exoplanets, these protoplanetary disks. This is HL Tau, an image from ALMA that came out last year. The most complex molecule seen to date there is methanol. It just came out in a paper a couple months ago. Methyl cyanide was out earlier than that, and we've also seen things like formaldehyde and water. Can't see anything more complicated than that yet, just because there's not a lot of those molecules there. They're very faint and hard to detect. But the molecules still play an important role in these disks. There was a paper out just about a month ago or so showing that if you take the small little dust grains that are coated in ice, you can actually start conglomerating them together, not as a large icy chunk like a comet, but sintered, like a sintered glass crucible, so that they have little connecting bridges of ices between them, and this allows them to aggregate into larger and larger structures. Now this hasn't been proven yet. This is a theoretical paper, a modeling paper that came out, but it's a very good theory for how you can overcome the barrier between small, icy dust grains and rocks, planetesimals, that'll chunk together to make these exoplanets. So speaking of exoplanets, this was as of 2 days ago when I went and got this plot from the Exoplanet database. Kepler, one of the main observatories that's been contributing to the detection of exoplanets. There are thousands of them here. This is a plot of orbital period, so how long it takes them to orbit their star, and the mass of the planet, and then this, I just picked the size of the dot to give the size relative to the radius of the actual planet. All right, so we have a lot of these relatively large planets over here that are around Jupiter mass, but we're starting to fill in the smaller mass, more Earth-like radius planets. Just to give a brief overview of a couple of the different ways that these can be detected. We can hope to do some direct imaging, but it's kind of really, really hard. Planets are not bright. They're hard to see. They're far away, and they tend to be embedded in dust from that forming disk. And it's really hard to see through a dusty gas disk to look at these planets directly. So we can play some tricks. The one that is used, as we'll see in a second on another slide, most commonly is this transit photometry. So you just put the planet in front of a star and look for the dip as that planet blocks some of the light. This is what Kepler does, and it's really good at detecting planets that are relatively large or that are small, but they have a small star. So you can see the dip that comes along with them. The only downside to this is that if you have a planet that takes 3 years to orbit your star, you only get one dip every 3 years. So you have to get lucky and be observing it at that point. And then if you want reproducibility, you have to wait another 3 years. So this is really good for short period planets, but it's a little harder for the longer ones, but we're starting to see them. And the last one that I'll mention is radial velocity measurements. So this is where you take a star here that you're looking at, and as it moves relative to the Earth, the light that we see from it is going to be Doppler shifted, right, red and blue. But if it has a planet perturbing that movement a little bit, that's going to perturb that Doppler shift that we see. And you can pull out a planet's perturbation of its own host star by looking at changes in the Doppler shift. And here's, I think, my last slide, because I am right on time to be done. Just a graph of the different ways that these planets have been detected over the last decade and a half, 2 decades there. You'll see that this huge bump in the number that we've detected from transit photometry, that's due pretty much exclusively to the Kepler telescope, which has been out hunting planets for a very long time now. Close second, well, distant second, I don't know, is the radial velocity, and then there's a little bit here for direct imaging. And there's a few other, I don't want to say niche, but niche detection methods, which maybe we'll hear about today and maybe we won't. Oh, very last thing, exoplanet atmospheres. If you are doing transit photometry, you are actually capable, if you're lucky, of getting an absorption spectrum of that planetary atmosphere as it passes in front of the star. So here's one. The red is a model. The black are the data points showing the absorption of CO, CO2, water in an exoplanet atmosphere as it transited in front of its host star, presumably over many, many, many averages of that data. So I think that is it. Yes? Thank you very much. We're right on time, so we can start the actual talks.